Here's a picture of myself and my father at a family reunion, and it turns out that the same year that I moved here to UC San Diego, 2011, I lost him to pancreatic cancer. And it turns out that he lost his mom to stomach cancer. And so as I had a chance to move to UC San Diego, where you have this great, not only great engineering school, but great medical school, I got curious about exploring not only doing neuroscience research of the brain, but also perhaps exploring the digestive system, knowing absolutely nothing at the time. And so as we start to bounce around, one of the things that we notice is that when you take a look at people who have digestive problems, nausea, pain, bloating, constipation, you could have a variety of all these different diagnosed conditions right here, and yet all of them overlap with the symptoms that I mentioned before. And it turns out that it's a very long process of you going from your primary care physician, perhaps to a GI specialist, to go along the treatment path to identify exactly what your problem is. And things with very overlapping symptoms can have different optimal treatments. And so altogether, it's a very expensive process. In fact, I learned that digestive problems are the second most common reason that someone misses school or work after the common cold. So one of the things that got interesting about this when I learned more is that the digestive system is not only sort of a mechanical type of system, but it turns out it also is an electrophysiologic system, and it's actually connected to our brain, for example, via our vagus nerve, and we know that there's a neurohormonal axis. But if we focus on the digestive system itself, it turns out that it contains over 100 million neurons, and it also contains a variety of other type of pacemaker cells that operate similar to cardiac myocytes. So, a little bit of basics of, if we focus on the stomach for the moment, how things work. When you first eat some food, the top part of your stomach brings the food in there, and it expands, and it turns out there are stretch receptors there that connect to neurons in our enteric nervous system, and they pass information to further downstream cells, the pacemaker cells, and these guys are coupled via gap junctions to our smooth muscle cells that elicit the squeezing. And so as the food goes downward after it's processed more into what's called chyme, these contractions occur, and ultimately they can go into the small intestines via the gateway called the pylorus, which is a sphincter just like in our bladder. So one of the things that we found is interesting about the digestive system from an electrical perspective, me, someone who's trained as an electrical engineer turned neuroscientist, is that there are neurons, as I mentioned before, there are smooth muscle cells, but in between, there are these pacemaker cells, and if we know Ramon E. Cajal, the Nobel laureate, so these are called the Cajal cells. He discovered these as well. So these are pacemaker cells, and they operate like neurons that when they cross a threshold, they generate action potentials. But what's unique about them is that they have this background slow wave that's operating very slowly at about 3 cycles per minute. And it turns out that that slow wave propagates downward along the stomach. And as we see here, when these action potentials get generated, that's what gives rise to the smooth muscle tension. So in a normally operating stomach, what we should see is we should see this slow wave of activity that's literally propagating as a propagating wave from the top downward, from the esophagus towards the small intestines. And so, the frequency is 3 times per minute, which is 0.05 hertz. Now, what's also interesting about our digestive system is we know the sympathetic and the parasympathetic system modulate this. And so, for example, parasympathetic is also called rest and digest. So it turns out that sympathetic hits the brakes on digestion, and parasympathetic hits the gas pedal on this. And another way to think, to simply remember this is stress and whatnot corresponds to sympathetic, calm corresponds to parasympathetic, and one of the things that occurs during parasympathetic is the heart slows and the gut speeds up. So this is a complicated system if there are doctors involved, because how can we determine if if the cause of their GI problems is because the pacemaker cells in your stomach perhaps are adversely functioning, or is it because the inputs via the autonomic nervous system, sympathetic and parasympathetic, are what are causing the problem? How can we sort of disambiguate this? So the high-level idea that we got is that we know that the EKG has been very helpful for the heart. Can we do something analogous by placing an electrode array over the abdomen to measure this electrical function to see what's going on with digestion? And so I was able to establish a collaboration with David Kunkel here in gastroenterology right when he showed up around 2013. And the first thing we did is we always learn from others. And so we asked ourselves, had anyone else had this idea? And it turns out people had. And so this idea got popular in the 1980s, and so people placed 3 electrodes over the abdominal surface One is ground, one is a reference, so it generates one waveform. And as I mentioned before, that the slow wave occurs at 0.05 hertz, and we know that the contractions increase more after you eat a meal, so a very natural idea is to build a time frequency representation, and let's take a look at before and after a meal. If we see more energy in 0.05 hertz after a meal, that means your stomach is operating normally, otherwise there's a problem. So that seemed like an interesting idea. This actually got popularized, a device got FDA approved, a billing code for insurance got generated in the 1980s. Then later in the 1980s, a bunch of negative papers came out. Papers that say things like poor correlation with, with the clinical gold standard, doubtful usefulness in adults. And so the punchline is that people tried to do this but didn't get any meaningful information. But I'm from Dallas, the Dallas Cowboys and the Dallas Mavericks. So we asked ourselves, well, hey, let's be cowboys about this and let's explore, perhaps there still is a way to use these types of techniques, and maybe that we can use some modern engineering tools. And so we basically found from what was popularized in the 1980s, which then got very unpopular, there were some key limitations, and we systematically tried to surpass them. One of them is there's a ton of anatomical variability. So if you look at these plots, these are 4 CT plots, and what I'm showing you are the stomachs of these 4 patients. What I'm also showing you is there's 3 red dots on each of those CTs, and that's the 1980s clinical perspective of where you should place the electrodes. And notice in the 2 middle plots, you're nowhere near the stomach. And so it turns out that noise in equals noise out, and if you're not overlapping the stomach, you're probably not getting useful information. Something else that occurs is that there are these very subtle muscle artifacts that occur when we place electrodes on our abdomen, and they generate huge artifacts. And so the latter, what I hope you can appreciate is that, PhD in electrical engineering, signal processing, we can figure out ways to eliminate the artifacts. I won't spend time telling you how we did that, but we can do that. And to address the question of the variability with the stomach, perhaps we shouldn't just place 3 electrodes, maybe we should place an array of electrodes. And so the high-level idea of how this works is we use a multi-electrode array, so for example, 2 centimeter spacing apart. We can actually use the same type of amplifiers that are used in EEG as long as they're DC coupled, because this is a 0.05 hertz signal of interest. It turns out these are also in the microvolt, so we can literally use EEG systems. And the movement artifact rejection algorithm that we developed, at a high level, what we exploit is that the signal of interest is at a known frequency of 0.05 hertz, and we have these sporadic time points where we have large artifacts, so we can develop appropriate estimation procedures. And what I'll show you is before the artifact, this blue signal, you don't even see a peak at around 0.05 hertz, but after we eliminate the artifact, you can see it very cleanly. And we developed a measure of signal to noise ratio, and at an individual level, each one of these dots is individual subjects, and we see an improvement in the signal to noise ratio. So something else that we decided that we needed to do from talking to my clinical colleagues is that we basically were not at sea level. We were below sea level because in the 1980s and then subsequently afterwards, all these negative findings came out that showed that a cutaneous array trying to measure digestive system is absolutely useless, doesn't correlate with clinical gold standards. So we want to take our new approaches and see if they do correlate with clinical gold standards. And so the clinical gold standard in GI, after your GI doc does an endoscopy on you and they see nothing, there's no problem, no cancer or anything, they will send you to nuclear medicine and make you eat a radioactive egg sandwich. And with this radioactive egg sandwich, they see how long it's in your stomach before it goes into your small intestines. And for a typical human individual, this should occur in about 4 hours. So you either have delayed gastric emptying or slowed gastric emptying. So the way this works is the imaging actually is completely passive. It's different than an X-ray. There's no exposure to radiation from the imaging. All the radiation comes from the radioactive egg sandwich. So we asked the radiologist, I said, you know what, well, rather than imaging at the 1 hour, 2 hour, and 4 hour mark, let's image every second, because then we can actually image the individual contractions. And we can simultaneously place our electrode array. And so we did that. And so we can get different images of the stomach, and where those little white arrows are correspond to contractions. It's not completely clear on this image. So what I'll show you on this top image is what we did is we built an ROI over a region of the stomach where the pacemaker cells are, called the antrum. And we just took a look at the average of the pixel intensities. And when you see in the top plot, you see clearly it's oscillating, right? The bottom plot is a waveform from our electrode array. And if you look at the frequency response of both of those, you see a nice peak at 0.05 hertz. If you look at the dominant peak up to the 3rd decimal place, the contraction information that we're picking from the clinical gold standard is commensurate with what we're picking up electrically. So this is just for us to showcase that what we're picking up is meaningful. It's the same as the contraction frequency that's captured with imaging with the clinical gold standard. Now, so we're able to solve the anatomical variability and the artifact issue, but it turns out there's something else crucially important, which is the spatial aspect. As I mentioned before, the slow wave is sort of propagating downward from top to bottom to help elicit those contractions to push food downward. Well, it turns out that that's not always the case. And so there was a landmark paper in a journal called Gastrodynamics, and as in many fields, just like in neuroscience, Neuron is a big journal. So in GI, there's a saying, right, in Japanese business cards, right, the shorter the title, right, the more important they are. So the shorter the title of the journal, the more important it is. So this is the biggest journal in GI, and so there was a study that was done where they had people that were doing a surgery for a variety of different reasons, not related to GI, and so you had a subgroup of patients who were normal and a subgroup of patients who had GI problems. They placed an array of electrodes right on the surface of the stomach, and so you can generate vector fields of the direction of the slow wave propagating. And what they found is for a typical normal subject, you see this picture right here, this beautiful trajectory from the esophagus towards the small intestines. Patient diagnosed with gastroparesis or delayed gastric emptying, you see something very interesting. You see the wave is actually initiated further downstream and it's bifurcating. So it's not surprising why you may have nausea, right, or gastric reflux, because the wave is propagating in the wrong direction. So the initiation point is further down. So we got very excited when we saw this because we asked ourselves, imagine if we could pick up this kind of information non-invasively. So we developed a very simple model where these pulses that are generating 3 cycles per minute, we basically mapped this to the 1D wave equation with amplitude specific, location specific amplitude, because we know that parts of the region of the stomach, the slow wave is higher amplitude. We then overlaid this onto, so we have CT scans of a bunch of our subjects, and it turns out there's lots of variability, and so we can map this 1D solution to the wave equation onto a stomach of a CT. And then what we did is we basically just simulated what the volume conduction would be from the surface of the stomach onto the abdominal surface. And what we see right here is we cannot pick up all the spatial details, but we can pick up the high level information about the wave. And then we simulated what would it be if we had a 5x5 electrode array. And you can see that qualitatively you can pick up some wave-like information. And so with that, we took the next step was we actually collected data on human subjects. And so with this 5x5 array, the types of waveforms that we see are like what you see right here. You can see very clearly across these 3 electrodes of different colors, you can see that there's a shift in the phase as you go along space. And so this is, the, in some sense, the signature of a wave, and we can generate nice videos that can basically showcase this slow wave propagation that's occurring along the stomach. We developed some appropriate signal processing tools, and in some sense, at a high level, what we're paying attention to here is less about amplitude and more about phase relationships across electrodes. And so with that, what we can start to do is to look at the direction that the wave is propagating. And something else that we were very interested in is the fact that if we collected a bunch of data, we just generated completely random noise, we might get something that looks like a wave. So can we develop some type of measure, a number between 0 and 1 that is large when we have a nice structured plane wave and is 0 otherwise. And so we can basically use Jensen's inequality and use a measure called the phase gradient directionality that's been used in physics also to characterize at every moment in time, do we see something that's wave-like? And if you look at this top green plot, you see most of those vectors for each electrode, the direction of phase change, are basically propagating to the left, slightly up or slightly down, whereas in the bottom, it's completely random. And so the PGD is 0.94 versus 0.41. So with this, we can now build a statistical significance test with bootstrapping to determine in what snapshots in time do we see a wave occurring. And then we can ask ourselves, when we see a wave occurring, what direction is it moving? Because we know it should be pushing towards the small intestines, at least for normal controls. And so we can build a spatial histogram. And so one of the things that we were able to do with a bunch of clinical patients here at UCSD is to take a look at controls versus patients with diagnosed GI disorders using invasive techniques. And so for a control patient, so we have CT scans on each of these patients, and we place the electrodes relative to the CT, and so we know the direction towards the small intestines. So we basically built something like a cone corresponding to towards the small intestines, and we look at what fraction of the waves are not propagating towards the small intestines. So we can do this at the individual level. And if you notice at the control, the spatial histogram has everything basically towards the small intestines, whereas in the patients diagnosed with gastroparesis, the direction towards the small intestines is here, which corresponds to here on the spatial histogram, but most of the statistically significant waves are going in every direction but there. So this is sort of very interesting, and this was not just a simple case where I took the best possible example. This is a plot from this is our first clinical journal that we're excited about. And what's fascinating about this is that it turns out in GI, just to give a sense of where it is compared to cardiology and neurology, is that as of now, there existed no objective measure that is non-invasive that correlates with the severity of symptoms. So this is kind of like when Marianne was talking about in her previous talk, where you want like a measure of mood and you'd like to have a physiologic representation that correlates with that. So what we're able to show here is on the x-axis is the percentage of time that the slow waves that are statistically significant are propagating in a direction not towards the small intestines. So propagating abnormal. So the percentage of time that bad propagation is occurring. And on the y-axis is very analogous to what Marianne was talking about. It's a clinically indicated score of the severity of symptoms. And so basically 0 means you don't have many symptoms, and 5 means they're very extreme. And what we can see very clearly is that this our measure correlates with the severity of symptoms. And just to so this is very exciting. This is our first sort of clinical paper on that topic, and so there's lots of opportunities to move forward with this. So one of the things that we got interested in next is, well, suppose I wanted to pinpoint the exact location of an abnormality, or at least into a high level detail. So suppose I split the stomach into 4 different regions. Could I pinpoint where this wave of initiation of abnormality is? And so in some sense, this boils down to solving an inverse problem, because we have a cutaneous array on the surface of the abdomen. Can we pinpoint where on the stomach the abnormality is? And so we were able to formulate this as an inverse problem, and with a CT scan of the individual, what we can propagate the potentials back. And I won't go through the details of this, but basically this is going to involve regularization, because there's many solutions that are consistent with what we observed. And one of the things that we use is a Bayesian inference tool, and smile to the students who just took my class here in the audience. We used a prior that encoded the fact that we want the activity to be smooth across time, and that's why we have a quadratic and the difference of the signal. But if you notice, we take an outer square root. And so the way to think about this is the square root of the square we know is the absolute value, and we know the absolute value encodes sparsity. So we're basically encoding sparsity in the coefficients, but encouraging them to operate smoothly over time. And it turns out that this is convex, and this encodes a convex problem. And we use these weights relative to a basis that corresponds to the spherical harmonics. Because if we think about the stomach, we know it's topologically equivalent to a cylinder. And if we think about a wave propagating downward, we could represent that very cleanly and sparsely if we use the spherical harmonics. And so we use the weights with respect to that basis, and we're able to leverage a recently published algorithm that is very highly efficient and uses a principle called IEEE, where this solution can be done very rapidly. And so ultimately what we're able to do is to generate a picture that looks like this, where the colors represent voltages. And so what you see is first the voltages on the cutaneous array, and then what we're mapping back is the activity on the surface of the stomach. And with this information, we segmented the stomach into 4 regions, and we're able to capture spatial statistics in each region. And this was, you can see more in a recent publication in PLOS ONE on this. So another step that we decided to explore, at least, is to understand, can we use some of these modern machine learning tools, such as deep learning, to be able to identify slow wave abnormalities? And so what we did with my student Anjali, and this is in Press in the Transactions of Biomedical Engineering, we basically took the multi-electrode array and we turned voltages into colors, and so that's like an image, but then we're measuring things over time. And so an image over time is a video. And it turns out there have been recent tools in developing video classification. And so we basically map these into that type of problem. And the takeaway lesson is that across a variety of tissue depths, as well as robustness to shifts in the array. So let's imagine that we don't have CT knowledge, so we don't place the array exactly over the stomach. And what we see is that there's quite a bit of robustness with horizontal and vertical shifts and getting strong accuracy. So the last limitation that we surpass with this, and this piggybacks off of Marianne, is just like how mood can go up and down, well, it turns out symptoms can go up and down. And so one of the things that happens quite often for patients is they get 3 to 5 months before they can finally get that referral to that GI specialist. They show up that day and they don't have symptoms that day. So whatever the GI specialist measured does not correspond to the symptoms that they felt. So we got interested in building, can we build an ambulatory system? So we don't just have to use the $30,000 EEG system that we started with. Can we build an ambulatory system and actually record people for 24 hours in the comfort of their own home? And so we were able to do that, and this is a great example of us completely riding our surfboards over the wave of innovation due to the BRAIN Initiative. So once the BRAIN Initiative arrived, there have been all these portable EEG systems that you can build, open BCI, all these different things. So we just took some of those tools, made sure they were DC coupled, performed some other tricks, and then just used them, and it turns out they work. And so we're able to build a multi-electrode array you can mount onto your body. We built a very simple event logging app, so when you have a symptom, when you have a meal, when you have a bowel movement or whatever, we can develop appropriate approaches to take the raw data, clean it up, eliminate artifacts, and associate it with events of interest. And so here's sort of an example of what a normal 24-hour pattern looks like. And so there's the time frequency plot, and we see that 0.05 hertz signal, the strength of that kind of ebbs and flows. It's not always the same magnitude. It's not always the same redness. And so in this next plot, what I'm showing you is the power at 0.05 hertz. That's what I call the EGG power. And we're just watching that over time in the vicinity of certain events. And we saw some interesting things that occur, for example, during sleep, where we see elevated power, and towards the latter stages of sleep, we see it starts to wane. We can also overlap this with a variety of different types of events. Now, one of the things that we got interested in, as I alluded to before, and we call this gastrodynamics, just like urodynamics, which they use in urology for 24-hour studies, is we can look at more information besides just the amplitude over time. Now, for example, let's focus when a meal occurs. We know that when a meal occurs, we should see an increased activity due to the contractions that are occurring. We can start to get a measure of how much that 0.05 hertz signal is above baseline and how it sort of wanes back down. And we can build a measure of area of, under the curve, and it turns out that this associates well with the notion of gastric emptying. Something else that we got very interested in is, remember that the spatial patterns are what correlate with symptom severity. So what we can now do is extract spatial patterns over time. And what's interesting about this is we can take a look at when this patient had a meal and when they had symptoms, and notice that when they had a meal around this time point, the arrow is pointing to the left, where arrow or left means anterograde or towards the small intestines. But notice in the vicinity of this symptom right here, the slow wave is actually propagating in a retrograde direction. So this is a situation where the slow wave abnormality is associated with symptoms. Now, one of the things that's quite common in GI patients is that a different cause of their symptoms could be something called visceral hypersensitivity. So basically it can involve an autonomic imbalance, and that can be measured using tools from heart rate variability and whatnot. And it turns out when we place these electrodes over the abdomen, we get the peaks of the EKG for free. And so with that, we can develop all sorts of state space models of autonomic function, and to look at things like the sympathovagal balance. And we can track these dynamics over time, and a ratio less than 1 means that it's parasympathetic dominated, and above 1 means that it's sympathetic dominated. And so we can start to develop ways to understand what the cause of these symptoms are. Is it the slow wave? Is it the autonomic function? These are the tools that we're now using to help our GI collaborators. And one of the things that we're proud of in particular is that we're able to actually solve a GI motility case that could not have been solved otherwise, according to my colleague. And the starting point is that I get a 68-year-old patient who had bloating in early satiety, retired aerospace worker, plays a lot of golf. It turns out his bloating is better in the morning and gets worse throughout the remainder of the day. His wife says that he looks pregnant at times, and he has the sensation of feeling overall full and sick. And what's interesting about him is that he's a type 2 diabetic, and he takes a variety of medications. Now, the diabetics aspect is interesting because one of the things we know about diabetes is that diabetes can affect your digestion, because neuropathies can occur, and you can actually build a neuropathy of your vagus, and that can be part of the reason that your digestion is abnormal. And so that always can be a confounder. So in any case, when they did the endoscope, my colleague couldn't even get the endoscope all the way to the bottom because it was filled with so much debris and fluid. Further, when they did the radioactive egg sandwich, the gastric emptying study, at the 4-hour mark, 80% of the egg was still there. So he was extremely delayed. Now, when you take a CT of the patient, you can see his stomach is just very expanded. And so the clinical workflow that he decided to go through is, should I give him medication to treat his diabetes? Should I give him a test for small intestinal bacterial overgrowth? Suggest a certain diet to reduce his IBS? Basically give him a pro-motility agent, so erythromycin elicits gastric motility. Or what happens quite often is that they can basically just give you something that'll treat the symptom, so an antidepressant. And so he said, well, also, let's try this new technology that, that Todd's group has been developing. And so we explored this on the patient. And so when we did this, one of the things that we saw right away, so remember the bottom picture is what a typical healthy control is. So there's this sort of ebb and flow. If you look at the magnitude of the red, of the 0.05 hertz there, it's just always on going gangbusters. So when my colleague saw this, he said, aha, this is a pattern of obstruction. That means that the digestive system is trying like crazy to squeeze. It just can't get it through for some reason. So he sent him over to pathology, and they got a piece of tissue towards the bottom part of his stomach. And indeed, they saw that he had an infection that typically you see in cows. So this is called a Sarcina infection. So very few of these infections have been seen in humans, but it turns out this is what the patient had. Luckily for him, so this infection, as you can imagine, sometimes can create lots of scarring and whatnot, and that scarring can block the food from going through the sphincter. Thankfully, once this information was obtained, he was referred to one of the top surgeons here at UCSD, and the surgery was done to basically cut out the part of the tissue where the inflammation is and connect the small intestines to that. And remarkably, here's what his stomach looks like before the surgery and after the surgery, not nearly as bloated. And that amplitude, that extremely gangbusters 0.05 hertz is not nearly as high as it was before. Most importantly, his symptoms resolved. So this is an example of our exciting opportunity with our 24-hour measure. We're able to do this. And what we're showcasing right here is across a variety of patients of different diagnoses. If we use the standard 90-minute protocol from the 1980s, 30 minutes before a meal, 60 minutes after a meal, these don't separate as well. But after we use our 24-hour study, they start to separate much more. And that patient that I mentioned before is that red dot that moved from the right to the middle. And so what I'm plotting is basically the percentage of time that 0.05 hertz is the top frequency across these bands. And what we see is that there's hyperactivity, hypoactivity. This corresponds to delayed gastric emptying, to rapid emptying. And so this further sort of communicates the utility of using a 24-hour type of tool. So the next steps that we're exploring with this are, well, one thing is that we built this ambulatory system, but it's still nice and kind of clunky. Can we go one step further? So our lab dibbles and dabbles with flexible electronics. You know, when I went as assistant professor at Illinois, we collaborated with John Rogers, and so we have some of these tools here at UCSD. And so we recently were able to build an adhesive integrated system that's just a patch that you place over the abdomen with an electrode array. One of the things that's tricky about this is that there's a saying, one man's trash is another man's treasure. We care about 0.05 hertz, which is almost DC. If you use gold, it's not going to work well because gold is so biologically inert that you're going to get this DC offset. And so we have to develop clever ways to get silver chloride into these types of formats. And it works beautifully. And so here's just a picture of the signal. See this nice peak at 0.05 hertz. We can extract these spatial statistics. One direction that we're going with using these tools in particular is looking at newborn babies. And so I've been very hesitant to play around with the microbiome until I had a very concrete question that I wanted to ask. But when we now think that we have a concrete question within the context of newborn babies, babies are fascinating, first of all, because they pee and poop all the time. So measuring the microbiome is not a problem. But if we take a look at newborn babies in the neonatal intensive care unit, they're preemies. And so it turns out that their digestive system in many situations has not been fully developed. And so with our electrical tool, as well as with measuring from the microbiome, we can actually watch how the digestive system is maturing. And what's interesting about the mechanistic questions that we can ask connecting the electrophysiology to the microbiome is that we can actually measure the dietary intake. And so one of our colleagues here at UCSD is one of the experts in building a digital description of what's in breast milk. And he had a recent discovery that one of the biggest things that's protective of necrotizing enterocolitis, which can kill babies in the NICU, is a certain component in breast milk, human milk oligosaccharides. So he has the tools where he can quantify. Imagine you could almost mass spec the hell out of some breast milk to understand exactly what's there. We can quantify the function of the digestive system, and then we can measure the output in the microbiome based upon the stool. We can start to understand what's occurring. And what's fascinating is that there's a feedback loop from the microbiome back to motility and short chain fatty acids and things like that, and ghrelin. And so we have an ongoing project with Rady Children's Hospital where we're using these electrodes. And these electrodes have to be designed very carefully because baby skin is very fragile. You know what the biggest organ on our body is? Skin. And the newborn's skin, especially a preemie, can be very fragile. So we had to make sure we built our electrodes using the same material that they routinely use in the hospital. And so this is an ongoing project with Rob Knight and with Lance Prince. And so this just sort of provides an example of some of the things that we're doing. And I'll say one other thing just in passing is that we actually are now monitoring response to treatments. And so there's a handheld vagus nerve stimulator that's FDA approved for migraines. And so a collaborator at Stanford is repurposing this, and she has an FDA clinical trial where she's using it to treat gastroparesis. Remember, the vagus corresponds to parasympathetic. Parasympathetic is rest and digest. It hits the gas pedal on digestion. Can we measure what the response is? And we have very nice preliminary data on that. And so with that, for the purpose of time, I'll just sort of conclude my talk. And so thank you.
Nobody has babies. Very fascinating work. So I guess we got very fascinating. So we have more, I guess we have more neurons in our guts than in our brains, right?
No, that's not true, no. But what is true is that, well, there's about 100 million neurons in our gut. That's about the same as in a cat brain.
Okay.
Well. About a cat brain. But one thing that is interesting is most of the serotonin in our body is made in our digestive system. So there's many connections about the gut-brain axis. It's so funny. We started working on this in 2011, and then the microbiome came out of nowhere, and it started sucking all the oxygen out of the room about the GI system. And so I've been very hesitant to not ride that bandwagon and wait until I have a very specific hypothesis. But now with the newborn babies, we feel good about really trying to interface the two together. But I think the electrical story is also very interesting, and so that is where our focus had been since 2011, and now we're overlapping it with the microbiome. Yeah. Terry.
So in addition to serotonin, almost every peptide was first found in the gut, like VIP,
Yep.
vasointestinal peptide. So it's a treasure trove of neuromodulators. And
I agree totally. And one of the things I find fascinating, so I mean, there's so many interesting areas to go into, but we know that one of the hottest topics right now is the opioid crisis. And so if you take a look at the opioid receptors in the brain, in some situations, they're even more densely populated in the gut. And so what that means is that if you want to see if someone is, issues of vulnerability to opioids, you actually might want to pay very close attention to the gut and not only the brain. Something else that's very fascinating, along these lines is we know that cannabis is being legalized in more and more states, and so it's legal in California right now. So my gastroenterology colleague, he has a lot of patients that, they use cannabis to treat some of their pain and whatnot. But one of the things that they're finding, this actually made the New York Times Sunday edition, is that some of these cannabis users are showing up in the emergency room with these extreme GI pains, and it's something called cannabinoid hyperemesis syndrome, and it creates these extreme excruciating pains in the digestive system. So it turns out that he has a bunch of patients who've experienced this and gone to the ER, and so we actually monitored them, and we had a presentation at the recent annual GI conference showcasing that slow wave abnormalities are associated with this condition. So this could also be used to determine who might be susceptible to adverse effects of taking cannabis. So I think there's many opportunities when we think brain, gut, because the receptors are in both, in some situations more densely populated here, they can be used for a variety of purposes.
Any other questions or
Dave had a
comments?
question.
Oh, sorry, I missed.
Thank you very much. Very good presentation. I'm waited for microorganisms in our digestive area. Finally, you mentioned about it. Because
my talk.
my reason here is someone doing something about microbiome flora related to the neuron or brain. It's directly related. Even the stressful cause of the stressful.
Oh, yes,
Or, yes, very strongly, and also control the immune system, immunosystem.
Oh, yes, absolutely. I agree totally.
And I'm so glad you mentioned about it. And in the future, many people are doing, because microbiota is so many different species, and anyway, I don't know how you can check it.
So-
or-
So
Yes,
I'm very
difficult.
thankful because here at UCSD, we have arguably the best microbiome group in the
okay.
world, with
Okay.
Rob Knight, the Human Microbiome Project. He's based here. So I always knew when the timing was right, we can push that button.
Yeah.
I just did not want to chase an ambulance. I wanted to
Okay.
wait
Yes.
until I really have a hypothesis
Okay.
to go and
Yes.
engage them. Now that I think we're reaching that point, I think we can really have lots of fun. And one of the things I think that's exciting is that there have been many studies with the microbiome that have associated, like diabetics versus controls, but it's unclear if there's like underlying etiologies or mechanisms. And so with sort of the electrical approach that we're taking, black box diagrams with feedback loops, we think we can be in a position to begin to think about mechanistic understanding so that we can know ways to perform manipulations, to perform improvements. And I think, as with anything, it's going to take perspectives from many viewpoints, immunology, as you mentioned, the hormonal axis, but also the electrical axis, and interfacing them all together. So yes.
Again.
That's fascinating, Todd. So the enteric nervous system is really interesting because it's primitively, it's evolutionarily incredibly primitive, right?
Absolutely.
And it's.
If you think about peristalsis, right, and
Yeah.
earthworms, it's the exact same mechanism.
And,
Sorry.
and almost independent of the brain itself. And it's just modulated to an extreme, right? That, are you aware of any work that's using the enteric nervous system as a model, sort of the human equivalent of C. elegans, right? In terms of modeling sort of information processing and interactions and.
Yeah, so we ourselves are beginning to play in that type of area because if you take a look at the field of neuroscience, the understanding of the enteric nervous system is not nearly as well established as of the brain area. And so there's lots of fun, very basic discoveries to be done there. And we ourselves, we find that could be an interesting place where we can play around because I've come from the neuroscience area and we can sort of come down. And so, for example, Terry's aware of this because a postdoc that was in his lab. Terry's lab has done some amazing work at characterizing wave-like phenomena and what the neural circuit underpinnings of that are. Clearly, wave-like phenomena occur in the enteric nervous system, and it's important because it associates with symptoms. Can we borrow some of those tools? And so Terry's former postdoc, who's now a professor of math in Canada, he and I now collaborate. We're exactly borrowing that. So I think there are huge opportunities to borrow the advances from the brain and apply them appropriately and with discretion to the enteric nervous system.
Okay, any other questions? If not, I would like to make a comment, actually. This is a fascinating work. We have been working on sudden infant death syndrome almost 20-some years. I think nothing terrifying for a mother to losing a child. So we mainly look at, for respiratory neural network, especially we had a hypothesis on the heating and nicotine could affect the neuron. But we never ever considered looking for GI for this. And that the hypothesis came, I was born in eastern part of Turkey. My sister died when I was 4 years old. So it's very, very important to look at the fetal development. I think it's, I was very, very happy seeing your research on at least to look at the GI system in addition to the brain development. Thank you so much.
Thank you.